The 3-in-1 Smart Car and IoT Learning Kit from SunFounder is a hands-on, all-included electronics kit that is perfect for anyone who wants to learn how to master the Arduino. The kit comes with an Arduino, 22 different sensors and modules, breadboards, jumper wires, and everything else you need to build a bunch of fun and interesting projects. Learn about robotics by building a remote-controlled smart car that can be controlled with an infrared remote controller, or drive on its own and avoid obstacles or fall on a line. Learn about the Internet of Things with a project that lets you monitor the temperature, humidity, and light level of a room from an app on your smartphone. And build a plant monitor that tracks the temperature, humidity, light intensity, and soil moisture, and displays it on your smartphone so you can keep your plants watered remotely. It's a super cool kit, and I had lots of fun building all the projects in it. So click the link in the description below to order the kit from SunFounder. In this lecture, we'll learn how to use two different types of interrupts. Hardware interrupts, which are triggered by an external event like the press of a button or a signal from a sensor. And timer interrupts, which are interrupts that are triggered by one of the Arduino's internal timers. But before we learn how interrupts work and how to use them, I just want to show you a quick example that demonstrates why they're useful. In this circuit, the yellow LED will blink on and off repeatedly. The green LED is controlled by a push button. The yellow LED is connected to pin 12 via a current limiting resistor. And the green LED is connected to pin 11 via current limiting resistor as well. One side of the push button is connected to ground, and the other side is connected to digital pin 7. I'll be using the Arduino's internal pull-up resistor, so I don't need to connect one here. Here's the sketch. In the top half of the sketch, we declare variables for the button input pin, the button LED, and the blink LED. We set the pin modes in the setup function. The button input is using the internal pull-up resistor, so I set the mode to input_pull-up. Down in the loop function, this block of code turns the green LED on when the button is pressed. And down here is the code that blinks the yellow LED on and off. It's commented out for now just so I can show you how the button should respond to pressing it. So the button turns on and off the green LED each time I press it. Okay, now let me show you what happens when I uncomment the code that makes the yellow LED blink. The yellow LED is blinking on and off just fine. But when I press the button, the Arduino misses a lot of the presses. Sometimes the green LED lights up, and sometimes it doesn't. This is what can happen when you ask the Arduino to do two things at once. When the Arduino gets to one of the delay functions, it pauses and can't do anything else until the delay is over. While it's delaying, it stops reading the button pin, so it misses some of the button presses. Let's fix this problem by using an interrupt. To make an interrupt, you first need to write a special function called an interrupt service routine, or ISR for short. The interrupt service routine will contain all the code you want to be executed when the interrupt is triggered. The interrupt service routine is created by typing void, then the name you want to give it. In the blinking LED example from earlier, I wanted the button to control the green LED while the yellow LED was blinking. so the button press will trigger the interrupt. I'm going to name this button interrupt. Now we can write the code that reads the button and switches the green LED on and off up here in the ISR. Interrupt service routine should be as short and fast as possible. If you use multiple interrupts, be aware that only one can be run at a time. Also, the millis, micros, and delay functions all depend on interrupts themselves, so they won't work inside of an interrupt service routine. And serial print doesn't always work inside of an ISR either, because serial data is transferred with an interrupt. However, if you need a delay in your ISR, you can use the delay microseconds function to achieve the same effect. Interrupt service routines can't take inputs or return values. If you have any variables in the ISR, like this one here for button state, it should have the volatile keyword in front of it. Declaring a variable as volatile prevents the compiler from optimizing it, and make sure that it's stored in the Arduino's SRAM instead of a storage register like other variables. Otherwise, the variable's value might not always be accurate. For example, if your program is currently running inside of an ISR, and the variable changes in the loop section, the variable inside the ISR might not get updated to the new value. The volatile keyword ensures that the variable is updated if it gets changed in another part of the sketch. Now, to trigger the interrupt service routine, we use the attach interrupt function. It goes in the setup section. The attach interrupt function takes 3 parameters. The first parameter is the interrupt number. The Arduino Uno has 2 interrupts, interrupt 0 and interrupt 1. Interrupt 0 is connected to digital pin 2, and interrupt 1 is connected to digital pin 3. A 1 or a 0 here will indicate which interrupt you want to use. But to make it easier to remember which interrupt is connected to which pin, there's a function called digital pin to interrupt that you can use instead of the interrupt number. The digital pin to interrupt function takes the digital pin number, either 2 or 3. So in the previous blinking sketch, I had the button connected to digital pin 7. So I'll need to switch that over to one of the interrupt pins. Let's say pin 2. So here I've moved the button input from pin 7 to pin 2. Now I need to change my button pin variable from 7 to 2. Pin 2 is stored in the button pin variable. So I'll enter that in here. Okay, the next parameter used by the attach interrupt function is the name of the interrupt service routine. I called it button interrupt, so I'll put that here. You don't need to include the parentheses. The last parameter is the interrupt mode. The interrupt mode defines the type of signal that will trigger the interrupt. There are 4 options: low, rising, falling, and change. If the interrupt mode is set to low, the interrupt will be triggered whenever the interrupt pin is low. If it's set to rising, the interrupt will be triggered when the signal goes from low to high. If it's set to falling, the interrupt will be triggered when the signal goes from high to low. And if it's set to change, the interrupt will be triggered when the signal goes either high to low or low to high. To switch on and off the button LED, we need to know when the button press goes both high and low. So I'll use change here. So now, all that's left in the loop function is the code that makes the yellow LED blink. The code that detects the button press and turns the green LED on and off is up here in the interrupt service routine. Let's see how this makes the LEDs react. Okay, the yellow LED is blinking fine. Now I'm going to press the button. So that's looking good. Every time I press the button, the green LED turns on. The Arduino isn't missing any of the button presses. Okay, now let's take a look at timer interrupts. Hardware interrupts are triggered by an external event like a button press. But timer interrupts are triggered by the Arduino's internal clock. Before we can really understand how timer interrupts work, we need a little background information on timers. Timers are electronic circuits built into the microcontroller that allow you to count the time. Timer interrupts are usually used to read or write to pins at regular intervals. For example, you could use a timer interrupt to get the reading from a humidity sensor every 5 seconds. You could also use timer interrupts to make a speedometer by measuring the time between clicks of a rotary encoder. They can also be used to generate highly accurate pulse width modulation signals, more accurate than what the analog write function can provide. The Arduino has 3 timers: Timer 0, Timer 1, and Timer 2. Timer 0 is an 8-bit timer that's used for the delay, millis, and micros functions. You probably don't want to mess with Timer 0 or it might break those functions. Timer 1 is a 16-bit timer, and Timer 2 is an 8-bit timer. It's okay to use these two. All 3 timers are based on the clock frequency of the Arduino, which is 16 MHz. Each clock cycle counts as 1 tick of the timer. Timer 1 is a 16-bit timer, which means that it can hold a maximum of 2 to the 16, or 65,536 counts, before it gets full. When it reaches 65,535, the timer resets to 0 and starts counting again. Timer 0 and Timer 2 are 8-bit timers, so they can hold a maximum of 2 to the 8, or 256 counts. The speed of the timer can be slowed down by using a pre-scaler value. By changing the pre-scaler value, you can adjust the length of the timer. The Arduino timers have 2 modes: pulse width modulation mode and clear timer on compare match, or CTC mode. Pulse width modulation mode can be configured to output a pulse width modulation signal. Clear timer on compare match mode can be used to trigger an interrupt when the timer reaches a preset value. To demonstrate how to use timer interrupts, I'm going to show you a project that has 2 blinking LEDs. This is what the circuit will look like. One LED will blink at a rate of 500 milliseconds, and the other LED will blink at a rate of 5 seconds. The typical method to blink LEDs uses the delay function, but that won't work in this case. So we need to use a timer interrupt to control one of the LEDs. There's a red LED with a current limiting resistor connected to digital pin 10, and a yellow LED with a current limiting resistor connected to digital pin 5. The yellow LED will blink on and off at a rate of 500 milliseconds. And the red LED will blink on for 5 seconds and off for 5 seconds. Let's take a look at the sketch. To make the programming easier, we're going to use a library called Timer1. You can go to this link to download the library zip file. At the top of the sketch, we include the library. The yellow LED will be blinking on and off fairly quickly, once every 500 milliseconds. But the red LED will be switched on and off every 5 seconds, a much longer time. So we'll set up the timer to control the red LED. In the setup section, we set Arduino pins 10 and 5 as outputs. The Timer 1 library can only use pins 9 and 10 for timer interrupts. So I'm going to use pin 10 for the timer interrupt. And I'll use pin 5 in the loop. Initialize is the function that initializes the timer. The argument of this function sets the length of time before the interrupt is triggered, in microseconds. 5 million microseconds is 5 seconds. With the timer interrupt library, the minimum interrupt period is 1 microsecond, and the maximum interrupt period is 8,388,480 microseconds. Next, we attach the interrupt service routine with timer1.attachInterrupt. The attach interrupt function only takes one argument, the name of the interrupt service routine. Down here I have the ISR, and it's called long blink. So I put that in the parentheses. So every time the timer reaches 5 seconds, it's going to call this long blink interrupt service routine. With timer interrupts, like hardware interrupts, it's best to keep your interrupt service routine short. Here I have the digital write function that toggles the LED on and off. Normally we would use the delay function to blink an LED on and off. But only one interrupt service routine can run at once. And since the delay function itself uses an ISR, it can't be used inside of another ISR. So we need a different way to turn on and off the pin. We already know that the digital write function takes 2 arguments. The first argument is the pin number, and the second argument is the value to write, either high or low. However, you can also take a reading from a pin and use that as the value to write. Remember that the exclamation point is the Boolean operator for not. So this says if the digital state of pin 10 is high, write it low. And if it's low, write it high. So each time this interrupt is called, it will read the pin's current state, then write the opposite value. It's a pretty useful way to toggle an LED, and it only uses 1 line of code. Now in the loop section, we have the code that blinks the yellow LED. This is how we're used to blinking an LED, using the delay function to pause between digital writes. This block of code will be running on its own, and the timer interrupt will be running on its own too. Let's see if it works. So the yellow LED is blinking once every half second, and the red LED is blinking on for 5 seconds and off for 5 seconds. So this is obviously a really simple example, but timer interrupts are useful in lots of other ways too. Instead of using the interrupt service routine to turn on an LED, you could use it to read a sensor at a timed interval. Or you could use it to trigger a 5-volt relay while continuously reading a sensor. In the next video, we're going to use interrupts to read the clicks from a rotary encoder. SunFounder is my go-to source for sensors, modules, and other parts for the Arduino and Raspberry Pi. They have a huge selection of STEM, robotics, and IoT kits, and lots of useful sensors and modules. Every product has an online tutorial with wiring diagrams and example code. They also offer free shipping on all orders, with no minimum. Give them a try at www.sunfounder.com next time you need to order some parts.